The Newton's laws of motion and the Newton's laws of gravitation remains unchanged under Galilean transformation, which is used in the so-called Galilean relativity. But have you ever thought what happens to these two laws when one applies the Lorentz transformation? The Lorentz transformation is used in Einstein's Special Theory of Relativity. So, let's discuss about it. Welcome to another session of our discussion in physics. This video is a part of a series on Introduction to General Theory of Relativity. We have discussed about Galilean transformation in an earlier session. If you are interested, then please check the link. Consider a particle P whose position with respect to an observer O is given by R vector. With respect to another inertial observer O prime, the position is given by R prime vector. If the O prime frame is moving with a constant velocity v with respect to the observer O, then these two position vectors as well as the elapsed times of these two observers can be related, as you see here. So by Galilean transformation, one refers to these two relations. Now let us imagine this particle starts moving with velocity u prime with respect to the observer O prime. One may now ask, what is the velocity of this particle with respect to the observer O? Using the Galilean transformation, we can easily find the relation for velocity between these two observers, as you see here. This rule is known as the Galilean rule of velocity addition. On the other hand, in Einstein's Special Theory of Relativity, one postulates that the speed of light is a universal constant. Clearly, as you see here, under Galilean rule of velocity addition, these two observers cannot have the same speed of light. Therefore, in special relativity, this rule of velocity addition needs to be changed. Now, this rule of velocity addition was derived using Galilean transformation. Therefore, it implies that the rules of Galilean transformation needs to be changed. In special relativity, the rules of coordinate transformations are known as the Lorentz transformation. If the observer O prime is moving with a velocity v along the x-axis with respect to the observer O, then the coordinates of these two observers are related, as you see here. Using the Lorentz transformation, we can now find the new rule of velocity addition, as you see here. As per this new rule of velocity addition, if a particle moves with a speed c in O prime frame, then even in O frame it moves with the same speed c. Now a question arises whether Newton's laws of motion and the Newton's law of gravitation have the same form also under Lorentz transformation. As you see here, unlike the case of Galilean transformation, the expressions for acceleration in these two frames are not equal under Lorentz transformation. Let us see what happens to the third law. In special relativity, no signal can move faster than the speed of light. Let us consider a moving particle which acts on another particle. If the force propagates at a finite speed, then by the time the reaction force comes back to first particle, it would have moved by some distance, even if small. So, the action and reaction cannot be in opposite direction. Clearly, the both laws of motion needs to be modified under Lorentz transformation. In lap frame O, the Newton's law of gravitation says that the force between two masses of m1 and m2 is proportional to the product of their masses and inversely proportional to the distance squared between them. See here, under Lorentz transformation, the distance squared between these two masses are not same in these two frames, unlike the case of Galilean transformation. In special relativity, Newton's laws of motions are suitably modified. The modified laws are referred to as the laws of relativistic mechanics. On the other hand, to have a relativistic analog of Newton's law of gravitation led Einstein to develop his General Theory of Relativity. you have enjoyed today's video, please feel free to follow other videos that are available here.